the invitation. So this is joint work with Yuga Iguchi. Has done a lot of the work actually. So he's a PhD student of mine that is close to finishing his PhD. AJ has done a lot of work on this, and Mohammed based at KAUST, I believe, he has done a lot of the. He has produced a lot of the numerical results. There's a paper we have. There's a preprint we have placed on archive. So for anyone interested in more details, there is this preprint we have there. All right, so let's see what this thing is about. So I will keep things simple. I believe that there have been some talks already about multi-level ideas. So the models of relevance here, they are going to be stochastic differential equations. So just to set up some notation here, so sigma 0 is the drift, and the other sigmas with a subscript 1 or more they are the diffusion coefficients. D is the number of Brownian motions. Capital N is the dimension of the model. Yes, this is the drift function, exactly as I was saying. And then the diffusion coefficient, if you put all the particular multipliers of the Brownian motions together, they make up this matrix sigma. And at the end of the day, we just want to, I will focus on what we have called the forward problem in the paper. So we just want to estimate some expectation under the true distribution of the diffusion at some time instance, at some finite time instance, capital T. There is something also, there's also the filtering problem that makes an appearance in the paper, and some of the results that I'm going to be showing is they will also involve the filtering problem. I will say some more things about what is this filtering problem when I show the results. All right, so this is the setting. And something that we have emphasized in the paper, in the contribution that we make in the paper, is that we take under consideration elliptic SDEs, as is let's say the standard setting. But we also take under consideration, we also make some effort to tackle hypo-elliptic SDEs. So in an elliptic setting, this matrix multiplying the Brownian motion essentially is positive definite, but it can be in a hypo-elliptic setting. This matrix is degenerate, and sometimes, so in this second bullet point here, sometimes one can rewrite the SDE in a way that it emphasizes the presence of a hypo-elliptic model. So here there is this zero component in the Brownian motion. So some of the part of the coordinates of this model, they are smooth, and the other ones, they have the roughness, let's say, of the Brownian motion. So that's the setting, and there are some definitions here. So the full dimension is capital N, and then you can start thinking about what is the dimension of the smooth component, and with subscript S, and the dimension of the rough components, and with subscript R. And because we consider both cases, this number of smooth components can be 0 in the elliptic case, or it can be allowed to be greater than 0. All right, that's the setting. This is a setting also considered in the classical work by Mike Giles. And let's see, I will slowly get into what it is that we have added in this literature. Some differential operators will appear in the expressions that I'm going to be showing. I mean, they look long, these expressions, but it's nothing else than some terms that appear when you apply Ito's formula. Essentially, nothing more than this. There is also this term that it will show up in the calculations. So these are the only definitions that we need, essentially. All right, so let's see. Okay, I will say some things about discretization schemes, because this is what this is where the multi-level idea becomes relevant. This is why these models are interesting in terms of providing a setting to use multi-level ideas, because there is a discretization error, there's a Monte Carlo error, and one has to play around with these two types of errors. And the multi-level approach provides a benefit for this when applied in this class of models in some cases anyway. All right, so we will take things slowly. That's the Euler-Maruyama EM. This is the label I'm using. This is the Euler-Maruyama scheme. So it's a very standard scheme here. So this bar process is meant to show that this is an approximation of the real dynamics. These are now the discrete time instances that they appear in the dynamics, and this is the increment of the Brownian motion. I'm just setting up the notation here, so it just, when you see subscript tk here, it meant to be the increment of the Brownian motion from the current time instance tk to the next one, tk plus 1. So there's a step. This is a step. This delta b tk is a step of the Brownian motion of size after you have a period of time delta that has elapsed. All right, that's the Euler-Maruyama scheme. It introduces some discretization error. Again, this is what makes things interesting in terms of the use of the potential use of this multi-level idea. Milstein scheme, MIL with capitals. I will be using this abbreviation a couple of times. So here there are a few extra terms. So one aims at a more accurate approximation scheme. So now there is the same component as the Euler-Maruyama scheme, the EM scheme, but there are some extra terms here. And in particular, this is the term that is this delta A pk term, the last one in the bottom expression. This is the one that makes things quite interesting. So let's see what is the definition of this term. The other ones, they are just increments of Brownian motions at different coordinates of Brownian motion. All right, so let's see what is this guy. So this last quantity there, it involves double integrals with respect to Brownian motions that they can involve different Brownian motions in a multivariate setting. So J1 can be different than J2. So there is what makes things interesting is that one doesn't have an explicit distribution for such a term. So we don't know what is the distribution of this term. So we cannot simulate from this variable. So the Milstein scheme is not explicit in general, unless there are some particular conditions satisfied by the SD model. This is what is called, for instance, the commutative condition. So if this bracket quantity here is equal to 0, then it so happens that if you go back at the Milstein scheme, this quantity here will disappear, and then it is not needed, and that's fine. I mean, with these Lévy areas that they don't show up in the Milstein scheme. But in general, it is going to be there. So we are looking at the general case, and it's a bit annoying that such a term appears in the discretization scheme. What's the benefit of including such a term? All right, let's have some definitions here. So we are talking about discretization scheme, so it's good to define some errors. So there is this thing called the weak error. So it looks at the discrepancy between distributions, between the approximation scheme at the time of interest, capital T, and the true process. And there is this alpha here, so there is a rate of decay with the step size delta, and something else is that it's going to play a role in the efficiency of the algorithms that I'm going to be showing, is the strong errors of beta here, and let's say it looks at the So now there is you have to look at both the true process and the approximate process. They have to be defined on the same probability space, and we look at the expected value of the square of the discrepancy, and this goes down also with delta, and there is beta is the strong error. So that's the order of the strong error. Typically, yes, I mean, typically books that look at strong errors, they might have some general power here, but anyway, for simplicity, I have just used 2 here. And yes, that's beta. All right, so let's have a look at these schemes, these simple schemes that I have showed. So in the case of the EM scheme, the Euler-Maruyama scheme, the weak error, so this alpha here is equal to 1. The strong error is equal, beta is also equal to 1. So that's a result that it can be found in standard textbooks like Loden and Platten. Similarly, there is a very well developed theory for the Milstein scheme. So again, the weak error is of order 1, but what you gain by including extra terms in the Milstein scheme is that the strong error is increasing. So now it goes up to 2 now. All right, another thing that is going to play a role in at the end of the day, we are going to be using some estimators of some expectations. These are going to be Monte Carlo estimators. A term that is going to play a role in everything I'm doing here is also the Monte Carlo error is going to play a role in the derivations. All right, this is just a simple expression of where at the end we pick a schemes and we pick a number of samples, capital M, let's say, from whatever scheme we are using from the terminal position that we get from the scheme. All right, okay. Yet another last one. I think this is the last one that I'm going to be showing. So yet another scheme that is going to make a presence here is this thing, the truncated Milstein scheme, which is nothing strange. There is in the standard Milstein scheme there is this term involving the Lévy areas that creates some complications. And what Giles and Spruce have done in their paper, in their 2014 paper, that in fact this paper has motivated a lot of what we have done in our own contribution. So what they have done is that they have just removed the terms that they have just removed the terms with the Lévy area, and they are left with this expression for the approximation scheme. So it's not exactly the Euler-Maruyama scheme. It's not exactly the Milstein scheme. It's something in between. They are losing something by doing that. So now the strong error of beta, if you remember for the standard Milstein scheme with the difficult Lévy areas, so beta was equal to 2, the strong error. So now beta goes down to 1. So you are paying a penalty. But what they have done in that paper is that they have done some tricks that when they plug in this scheme in a multi-level setting, somehow they recover beta equal to 2. All right, let's see. I will explain step by step how it is that they did that and how it is that we have done that as well. All right. I was wrong to say that the previous scheme was the last one. So this is the scheme that it refers to our own contribution. So this is the second order weak scheme. This has been developed in a paper by my student Yuga. He's the main contributor in all this work. And myself and Matt Graham, a colleague from UCL. So the idea in that paper was to come up with some schemes. It was not so the problem there had nothing to do with multi-level algorithms or anything like that. It actually had to do with statistics. So to try to come up with we were trying to come up with some approximation schemes that they can be used in to approximate the transition density of SDEs, and then estimate parameters in a maximum likelihood estimation setting. But it turns out that such a scheme has some relevance also in this multi-level setting. All right, let's have a look. So the first component here on the top line of this scheme is the standard part from the Euler approximation. There is a delta eta component. There is a delta A tilde component. There are some definitions here. So it just so happens that we have tried to merge. We have tried to provide a single expression that covers both the elliptic and the high elliptic and the hypo-elliptic case. For something that it is already defined on this slide is this A tilde term. So this involves the original Brownian motion, let's say, from the SDE model. Plus there is this delta, this B tilde process, and the increments of such a process. This refers to an extra Brownian motion that is independent of the one that drives the stochastic differential equation. All right. Otherwise, there is this eta term that this is where we have to separate we have to give a different expression for the elliptic and the hypo-elliptic case. So when the dimension of the smooth component is equal to 0, when NS is equal to 0, we are in the elliptic setting, and otherwise we are in the hypo-elliptic setting. And these delta etas are defined in the next slide. All right, there is some particular expression. So this looks like a term that appears in the Milstein scheme. Otherwise, in the hypo-elliptic case, it so happens that because the model is a little bit particular, this term looks a little bit different. So it includes some integrals like this. So some double integrals with respect to Brownian motion and time, or vice versa. At the end of the day, just these are all Gaussian variables here. This except from the term at the top, these double integrals here, they involve some Gaussian distributions. All right, what's the point? I mean, why did we bother with this weak 2 scheme? It has a higher, so it increases the order of weak convergence. So here alpha becomes equal to 2 now. Before it was 1. It doesn't increase the order of strong convergence. So beta is still equal to 1. And I'm referring to to a textbook here by Milstein and Tretyakov. This is this book describes all the theory that we have used to derive this scheme. It's essentially what one has to do is do some moment matching. So one has to match some moments of the original process. And this by doing that, one increases the order of weak convergence. All right, so A is equal to 2 and beta is equal to 1 for the weak 2 scheme. All right, let's see all this alpha and beta. So all these alphas and betas, they are going to make a difference when we are in the multi-level context. I will explain briefly some things about the multi-level idea, mostly to set up a notation essentially. So I just have a few things added here. All right, what's the idea? So multi-level Monte Carlo, MLMC, so it is relevant when you discretize something, and SDE, as it is the case in this talk, or it could also be a partial differential equation, and there has been some work that myself and Ajay has been involved, where we actually look at even PDEs, and we apply, we study multi-level approaches. And then there is always some sort of a resolution parameter, delta L. We have seen this parameter appearing in all these schemes, this step size parameter appearing in all these schemes that I have shown for stochastic differential equations. And such a step size gives naturally, it gives rise to a sequence of distributions, or let's say the random variable of interest, which is the terminal position of the stochastic differential equation, its position at some time horizon of interest capital T. And we want to approximate the expectations under the theoretical thing that would have used infinitely many levels, right? So that's this theoretical quantity is the target. If one is to apply standard Monte Carlo, then what people would do is that they would fix some delta, or equivalently, they would fix some 2 to the power minus capital L. So they would fix some capital L, and that would induce some bias, and then they would just sample IID, they would just get IID samples for this particular choice of step size. So then it would be a matter of balancing the bias with the variance. In contrast, MLMC, what it does is that it uses samples from all different levels, and it combines these samples in a clever way. So let's make things concrete. So that's the SDE, a simple example of an SDE. Diffusion coefficient here is unit, and that's the simple Euler step, and then that's the step size delta L. That's the process. There is an extra subscript here. So there is the time at which we consider the process, and calligraphic L, this is the level that we consider. I mean, there's also an L0 here that is, I mean, one doesn't have to start necessarily from a step size of 2 to the minus L. One can start from a smaller step size. All right. This is the setting, a little bit of notation here. So this is the expectation of interest, the expected value under the correct distribution of X at time capital T. And just to make life easier, we just write also this expectation as eta infinity of the test function phi. All right, let's forget multi-level for a second. Let's see at standard Monte Carlo what would someone do. This is what I said a few minutes ago. So one would pick a capital L for a level, would sample IID with a particular step size, average the samples, and that's it. And there's a very simple error cost analysis. The mean square error is the square of the bias. This is where the weak error of the approximation of the SDE makes a presence. So there is an alpha there. And then there is the variance, which is, it goes down as 1 over NL. And there's a computational cost also, that it is equal to the number of samples n capital L times the computational cost, which is inversely proportional, essentially. So this zeta here is going to be always equal to 1 in our derivations. In a different context, in an SPD context, for instance, it might have been larger, but here is 1. All right, this is what the last bullet point says. So zeta is equal to 1, but also in this example, I'm using the Euler scheme, alpha is also equal to 1. So what's the bottom line? So let's say that we want to get an estimate that it is epsilon close to the true quantity, so that the mean square error is epsilon squared. This means that we need to have a bias, which is epsilon itself. So this means that this delta, the step size has to be selected as O epsilon. And then we have to make also, we have to balance this with the variance, the Monte Carlo error. So the Monte Carlo error also has to be of order epsilon. This means that the number of samples n has to be epsilon minus 2, or size epsilon minus 2. So the total computational cost is epsilon minus 3. So that's a very simple error analysis. It's not extremely satisfying because epsilon minus 3 is not that small actually. So what is that the multi-level does? It looks at the whole, it applies a telescopic sum, and it looks at the whole sequence of probability distributions for different levels. And it looks at the differences essentially between two consecutive levels, and there is a quantity there to be estimated, d at level L, which is a difference. And it's extremely intuitive that this quantity gets smaller and smaller, and we can produce unbiased estimators of this quantity. There is already a coupling involved in this difference, in the sense that I have to have these two random variables at level L minus 1 and at level L defined at the same time on a single probability space. And this happens quite in a very simple way in the context of SDs, just by using the same Brownian motion for both samples at the two different levels. All right, and then we have this multi-level estimator where now we are estimating each of the differences in the telescopic sum. And the idea is that since each of these differences is small, maybe we don't need, maybe this n, this number of samples can be quite, it can be quite small. So as the level increases, we need a smaller and smaller number of samples. That's the idea. There is again some cost error analysis that it is again not that complicated. So that's the estimator at the top bullet point. Yes, there are some simple details here. And then at the third bullet point, there is a simple analysis of what is the variance of this estimator of the y hat ml. The variance is simple because I have assumed independence across the various differences, and also for each single difference, IID samples. So the variance is quite simple. And this VL term, the variance at each difference at level calligraphic L, this is the critical term. This is going to make it, this is the behavior of this term is what makes the multi-level algorithm interesting. And then there is the computational cost, which it is also simple there's a simple expression for it. And there's a degree of freedom here in all this idea, which is how it is that one chooses the number of IID samples at each level, and this is what this can be optimized. So there is a constraint optimization that one can use that gives an optimal allocation of NL, the number of samples at each level. This number can be optimized, and not surprisingly, it depends on the particular choice of it will depend on VL, the variance for a single single estimator of a difference, and it will depend on the computational costs here. All right. So in general, one can get some expressions. One can characterize the variance for an estimator of each difference at level L. The computational cost, zeta is equal to 1. The bias again is going to play some part. So this age should have been delta. And for instance, in the EM case that I'm considering here, and in zeta will be 1, as it's going to be always in this talk. Beta is equal to 1 because it's very easy to control the variance of the difference, the second moment of the difference, just by using the strong error of the Euler scheme. And then alpha is the order of weak convergence, which is 1. All right, so a small comment here is that when we try to identify this guy here and say that, this beta is equal to 1, so which is the same as saying that VL, the variance of a single estimate of a difference at 2 consecutive levels, goes down as linearly with delta with a step size. And one adds and subtracts the correct solution, the correct position, let's say, of the STE at time capital T, and then and then one treats each of the 2 terms separately and uses the definition of the strong error to actually find that VL goes down linearly with delta. In the case of this antithetic multi-level thing that I'm going to be showing, one should not use this trick. So one has to study the difference, these differences at consecutive levels a bit more carefully. All right, a bit of more details. So yes, there's an optimal allocation, which is this. NL is once someone solves a constraint optimization problem, some Lagrange multipliers, essentially nothing more than this. So then one obtains some particular expression, and it so happens that there is some error analysis here. So I think I will focus on the last big bullet point. So the bottom line is that if the order of your strong error is equal to 1, is equal to Z, which is equal to 1 for the purposes of this talk, then you're doing well. I mean, the mean square error, to have a mean square error of order epsilon, you have a computational cost, which is epsilon 2 times you pay a penalty, which is the square of log epsilon. So there is an extra cost there. For any beta which is greater than zeta, so if beta is greater than 1, then this is nice because one gets what one can understand as the optimal, let's say, the optimal computational cost for standard Monte Carlo methods. So one is getting an algorithm that is epsilon close. The estimator is epsilon close to the true value with a computational cost that it is epsilon minus 2. It's the same as if one could get IID samples from the correct distribution of the terminal position of the SDE without any discretization error. That's as good as it gets. So any beta that it is greater than 1 gives this nice result. All right. Okay. So now let's have a look at this antithetic multi-level Monte Carlo. So it's a bit of a more recent addition in the toolkit of multi-level methods. So remember there was this Milstein schemes. They had a better strong error, but they involved some Lévy areas, and one was losing something there in terms of the strong error of convergence. This beta was getting lower, and we somehow do a trick that increases this beta. Let's see. Okay, the very simple picture here, which is meant to serve as more or less a definition. So there is there is a grid that looks at, there will be some ideas here that they will involve a coarse, the concept of a coarse grid. This is why there is a C here at the top. And then there is the level L-1. So here it's this is the step size, and k t with subscript k means that we have done k steps of such a size. And then there will be the concept also of a fine grid that it adds. So the fine grid here corresponds to the red x's. So that's the fine grid, and the coarse grid is the corresponds to the green lines. At least when we are talking about consecutive levels. So the coarse level at the coarse grid at level L minus 1 will correspond to the green lines for a particular choice of calligraphic L, and then the grid at the fine grid at level L at one step of a final level will correspond to these red crosses. All right. Okay. So let's see what's the whole idea here. Okay. So we look at the coarse grid, the green lines. All right. So in the fine grid, we will add some intermediate positions for the process of interest. This is the weak 2 scheme. This is the scheme that let's say we have come with. So it has a weak order. It has the order of weak error is 2. Okay, and if you remember, it involved increments of the Brownian motion, this process delta eta, and this delta A tilde that it had the product of the original Brownian motion times a second independent Brownian motion, and this delta eta, in the elliptic case, it involved some products of the original Brownian motion. In the Hypo-Elliptic case, it was a little bit more involved. It had this particular double integrals that it was an integral, some double integrals not of Brownian motions, but of a Brownian motion and time, or vice versa, time and Brownian motion. So some Gaussian variates at the end of the day. Okay, that's I'm just restating here essentially the expression of the weak 2 scheme. I'm just thinking now of this particular grid, this thing that we call coarse grid. Okay, and then someone start doing playing tricks here with these schemes. So before, you will notice that there was +1/2 here. That is the standard way that people apply the scheme. But then there is this thing called the antithetic. So the bar has changed into a tilde here. So this is the antithetic version for this process on the coarse grid. And then this process has a minus here. As a distribution, this doesn't change the distribution of the scheme, because remember, this A tilde term was the product of a Brownian motion plus an independent Brownian motion. So adding minus at the front doesn't change the scheme at the end of the day, but it will make a difference. In fact, we will see why this is the case. All right, this is what I say in the last bullet point. So in a distributional sense, adding a minus at the front doesn't make a difference. Okay, now we're going at a fine grid. So now we have to, I have shown one step of the coarse grid. Now I have to make a step of the same size as the one I have shown for the coarse grid. I have to make 2 steps at the fine grid, because we add an intermediate point. So this is why it says here, step 1. Okay, so we are starting, let's say, at the same position as in the case of the coarse scheme. And then there's nothing strange again here. We just apply the weak 2 scheme. That's it. It's just we apply it for half a step. And then we need another half a step, so that we make a step of the same size as with the coarse scheme. But now, again, there will be an antithetic version of this process. So here, let's see what it is that has happened in the antithetic version. So here, there's something funny that has happened here. So in the standard scheme, when moving from tk to tk plus a half, so when we are making the first step, we would have used the Brownian increment to go from tk to tk plus a half. Here it's the other way around. So it's like in the antithetic version of the fine process, we borrow the increments from the second step of the non-antithetic version of this one. So now we borrow the increments of these increments from the second step to use them in the first step of the antithetic process. All right, and also we still add this minus a half in this term, in this tilde term. This trick of switching the order in the consideration of the increments, this is the one. This was used in the paper by Spruce and Giles. So we have borrowed this idea from there. It so happens that this idea also seems to work for our own weak 2 scheme, our own discretization scheme. Again, in something which is new in our case is that there is this switching the sign in front of 1/2, that it was not there. There was not such a term in the Giles and Spruce paper. All right, so all tricks really. So and they're not random tricks. So they induce some particular cancellations, let's say. So let's have a look. So that was the one step, because I need to make now 2 steps to reach at the same position as with the course level and as with the course scheme. So now this switching of in the order of consideration of increments has been completed. So now in this antithetic version of the scheme, in the second step, we are using the increments from the first step of the regular non-antithetic version, let's say. Okay, what's the point here? Let's see what is the final scheme here. So that's the classical, that's the typical multi-level telescopic sum, and nothing more than this. And what we are actually considering in each of these terms in the telescopic sum, so there is the one term that involves the coarse level and another term that involves the fine level, is an average between the simple scheme and its antithetic version at fine level, and similarly at the coarse level. I have highlighted this term in red because in the Spruce and Giles paper, they didn't have to do anything funny with the coarse level. They just used there was no antithetic version at the coarse level. In our case, we have to use an antithetic version to treat some terms that they were not there in the Giles and Spruce paper. So yeah, we have to be a little bit more careful. And this is where we are. Okay, so let's give a name to this process that considers the averages. So let's call this process hat. So there is a hat process. It takes the average between the simple scheme and its antithetic version, both at the coarse level and at the fine level. And let's do some error analysis now of this difference in the multi-level telescopic term. And this analysis here, I think one can simply focus at the case when p is equal to 2. This is the case that can give away the main ideas, to be honest. There are 3 terms here. We have just used a Taylor expansion, nothing more than this. So this is what I'm saying at the last bullet points. And then you get some upper bound of 3 terms. The 2 last terms will be very simple to manage. So one simply uses the strong error of the scheme. It's already, if p is equal to 2, they are already something at power of 4. So it's something which is quite big, so that they will not, it's fine, they are quite small, these terms. The most important term will be this guy at the top. So it will be the difference of the average process at the fine level and the coarse process at the at one level before. All right. So as I promised, simply using the simply adding and subtracting the correct process, one can treat the two of the 3 terms in this upper bound, and the last term is the one that needs a little bit of work, and where all the tricks with the change in the signs and the switch in the increments, in the consideration of the increments of these Gaussian variables, this is where there's going to be an effect. But just notice that this theorem does the job somehow once proven, because for p equal to 2, so you get a delta to the power of 2, so beta is equal to 2. I remember there was this discussion I made a few minutes, 10 minutes ago, that if beta is greater than 1, we have mean square error epsilon with an effort epsilon minus 2. We just need this beta to be 2, okay? And this theorem gives this nice result. So this is the critical term. This is the term where things can go wrong if you don't do these tricks with the signs and all these things. And it so happens that by doing these tricks, let's see what happens. So here I have just composed the 2 steps at the fine level, so that I bring them, I bring them at the same level with the core scheme. And they look like this, all right? This is the regular version. All right, some calculation. I mean, I will just, and this is the antithetic version. I'm switching here the slides, and you see that there is this difference in the signs now that that our trick has introduced. So there will be some nice, convenient cancellations happening there. So that's all nice, and indeed these cancellations have happened, and some terms now have gone into this small guy that it's small enough so that this beta still remains equal to 2 when everything is taken under consideration. And similarly at the coarse level there are some nice cancellations happening, and you see at these 2 processes for which we will take the differences, they are for one step, so in terms of the local error, they are quite close to each other. So indeed, with a little bit more effort and way, one can get this result. Beta is equal to 2. That's it. Fantastic. So it is as if one has an algorithm that it is as if the Lévy areas have been actually used. And this has been achieved without using the Lévy areas, but by doing these tricks with the signs and the switch in the order of the order in the use of the Brownian increments. All right, we have some something I should mention here before I'm close to the end, is that our difference compared to the original paper on these antithetic ideas of Spruce and Giles is that we still have the same mean square, the same computational cost to get within epsilon from the correct quantity. So it's epsilon minus 2. The extra thing that we have in our case is that the alpha, the order in the weak error, is equal to 2 in our case. So let's see, I will make an extra comment on this as I saw the results. Well, let's see, let's have a look at some results. So I didn't say too many things about that, but we in the proofs and everything, one has to make some extra effort because of this consideration of the hypo-elliptic SDEs. So the first example in the numerics involves indeed the hypo-elliptic SDE. And the second example, it involves a regular elliptic SDE. I think this example was also used in the Giles and Spruce paper. And then I'm showing some results here. So at the bottom line is the mean square error. So the mean square error decreases as you go from right to left, and the vertical line is the computational cost. So in the blue is standard Monte Carlo, so no multi-level idea. In the orange is multi-level Monte Carlo without any use of an antithetic trick. So we are losing something there. And then it's in the purple, it's our method, this antithetic multi-level Monte Carlo idea for our method. So indeed, we can see numerically for this hypo-elliptic model, this FHN model, that we get for the same mean square error, we get we have a smaller computational cost. And here we have added the graph at the bottom. It just focuses on two methods: the one from the Spruce and Giles paper, and the one in the Spruce and Giles paper. It's the approximation scheme is a truncated Milstein one, and in our paper is this weak 2 scheme. So we get a benefit. There is a reason for this. It has to do with the fact that at the end of the day, for a finite epsilon, one has to choose some number of differences, some capital L, some number of levels in the scheme to control the bias. So in our case, this guy tends to be smaller than in the case of the truncated Milstein scheme, because the weak error is the order of the weak error is 2. Whereas in this truncated Milstein scheme is 1. So it's not a coincidence that we do a little bit better compared to the algorithm in the original paper of Spruce and Giles. And then there's the Heston model. We also get a similar picture. And the last thing that I will say is that AJ has done a lot of work. She has a lot of nice papers on getting this multi-level algorithm to work in a filtering setting. So this is not this forward problem anymore. This is the filtering problem. So things are quite more involved here. So there is sampling. There is a lot of things happening here, and all these things, they have to be coupled at 2 consecutive levels. So it's a very nice work actually, and some very nice proofs in the papers of AJ. Something that happens in this problem is that the error, there's an extra log epsilon square that gets into the cost of this for the filtering problem. It is just there because the method is more complicated, and this has been proven for the multi-level, for particle filtering multi-level algorithms that they actually use the truncated Milstein scheme. We have not proven such a thing for our weak 2 scheme. We just show numerically that it seems that this is still the case. So it still has a similar behavior as for the forward problem. So we seem to have the same error for the same computational cost. And again, we get the benefit due to this higher weak scheme. All right, and similarly for the Heston model in the filtering problem. So we are still doing better compared to the alternatives that I'm showing here. Okay, that's it. Thank you very much. Thank you.